Okay, part 4 of lecture 6. This is my least favorite slides of any slides that I present for any of my classes. There's something about it, this section, the next 10 minutes, that just feels like a fast one's being pulled, and so every year I know that it's coming every time I teach this class, and I look at the slides for a long time. I'm like, yeah, okay, it works, but every time it just seems tricky to me. So here we go. First, this is going to come up later. Oh, great. What is the context? The context is we just did the video, part 3, that constructed a camera frame, and now we're going to construct a 4x4 matrix that transforms points from the Cartesian frame, world space, to the camera frame. So we want to construct this 4x4 matrix, and of course we're going to use it now that we know the camera frame. And the derivation, again, I always find tricky. So this is going to come up later, and just in terms of what this means. So this is another way of thinking about coordinates in their Cartesian frame, typical world space coordinates. And so in the Cartesian frame, you have 3 basis vectors: the unit vector in x, the unit vector in y, and the unit vector in z, and then everything is relative to some origin. And so if you have some coordinate x, y, z, and it's relative to the origin 1, then this is a 1x4 matrix, and this is a 4x1 matrix. Now, it's a 4x1 matrix whose elements are made up of vectors, and this is a 1x4 matrix whose elements are made up of scalars. It works, but it's a little weird. And so if you multiply these two together, what you really get is you get a scalar times a vector plus, which a scalar times that vector, which is equal to the vector x, 0, 0, and another scalar times a vector y times 0, 1, 0, and that's equal to this vector, and so on. And then if you add the 3 vectors together, then you get the vector x, y, z, and if it's relative to the point 0, 0, well then you've got some point. Here's the point 0, 0, the origin, and then you've got some vector that goes in the direction x over and y up and z out, and this is the origin. And so this final thing, the vector x, y, z relative to the origin, is exactly the coordinates x, y, z. But it takes a lot of thinking about the machinery underneath. Look at my face. I can see my face in there. I'm like, it takes a lot of thinking about the machinery underneath the covers. And but I'm going to use this in a bit. That if you take the 1x4 matrix x, y, z 1 and of scalars, and you multiply by the 4x1 of vectors, which is the Cartesian frame, then it gives you the location x, y, z. And of course there's kind of some circular stuff in here because x means x times this unit vector and so on. But there's going to be a moment where we're going to see some math like this, where we're going to take coordinates like that and multiply it by a frame and get out the same coordinates or actually different coordinates. And so I just wanted to do some talking about that because that's part of why I've always been so uncomfortable with this derivation. Let me remove all this stuff. Okay, so here we go. So we've got 2 frames, and so the input frame is in world space. It's the Cartesian frame, and then the camera frame is the one that we described in video 3. And of course this says O, and it actually means the camera position, which may very well, in fact almost certainly, is not 0, 0, 0. And so the camera frame is a frame. So let me say it again. Camera frame. A camera frame is a frame. And so a frame means that we can express any vector in Cartesian as in the Cartesian frame. I'm just going to say any Cartesian vector as a combination of u, v, and w. And when I say Cartesian vector, I just mean that we're going to have some origin and some vector, and it's just a direction. And so any vector can be represented as a combination of u, v, and w. And the reason that any vector can be represented as a combination of u, v, and w is because the camera frame is a frame, and that's what it means. It means that we've got an origin, and we've got basis vectors that are linearly independent, and they span the space. And so if we talk about any Cartesian vector, we can represent it with some linear combination of these three basis vectors that help to make up the camera frame. And so now here's where it's the first step to what makes me uncomfortable. This part's cool. I'm fine with this. There's a lot of words here, but it's just the same pattern over and over again. And so we're just going to focus on this first pattern, and then we'll just look and see that the next two patterns are very similar to the third pattern. The final one's a little different. So what this says is if you got some Cartesian vector, and in this case the vector 1, 0, 0, the x, this is a basis vector for the Cartesian space, it can be represented as some combination of the basis functions of the camera frames, basis functions u, v, and w. And so this is a nothing statement. All this says is if you want to represent this vector, which is just a vector that's just an arrow like this, that you can represent it with u, v, and w. It might be that u goes like this, and v goes like this, but that you can represent this one, 1, 0, 0, with some combination of this one u and that one v, if that's where u and v are, because the camera frame's basis functions are not going to be the same as the Cartesian frame's basis functions. And we did a lot on Thursday kind of convincing ourselves that's true, that if we've got some vector we want to represent, as long as these two are not collinear, then or that our set of basis functions isn't collinear in some way, then we can do it. And as long as, in fact, I shouldn't say collinear, as long as they are linearly independent, then we can do it. And that's what it meant for it to span the space, that for any vector we can find some combination of these two vectors. And so that's a nothing statement, and all I'm doing here is just saying, well, it's got to be true, and what are the coefficients? What are the weights we place? What times u plus what times v plus what times w? Well, I don't know, so I'm just making up variables: e11, e12, e13. That's all that we're saying in this first statement, is that the x-axis in the Cartesian vector can be represented as some linear combination of the basis vectors in the camera frame. And if that's true for x, it's true for all the other vectors too. So for y, the same deal. Of course, the coefficients are different. So now I'm using, instead of e11, e12, e13, I'm saying e21, e22, e23. And for z, 0, 1, 1, the same deal, and just different coefficients. And then there's another vector, which is the Cartesian origin minus the camera origin. And I can just take the difference of those two locations, and the difference of those two locations is another vector. So sure enough, I can just calculate some coefficients for this vector right here, the Cartesian origin minus the camera origin, and I don't know what the coefficients are, but I know they exist to represent this vector. And at the end, I add O to both sides of the equation, and instead I'm saying, well, instead of this vector, I want this point to be represented as the same vector plus the origin for the camera frame. And I think I'm even going to put the words frame here. It makes me feel better. Camera frame, Cartesian frame origin, and camera frame origin. And we'll make that smaller so it all fits. And so really I've just set up these equations saying that I know that all these equations can be true if I have the right coefficients. And so then here's the next step in this derivation, is that I can put these four equations, one on top of each other, and then say, well, actually I can represent this as a matrix. And so this matrix says that 1, 0, 0, great. Sorry, I thought I had it wrong. I'm going to let it roll. I'm not going to restart. It says that 1, 0, 0 is equal to E11 times U plus E12 times V plus E13 times W plus nothing times the origin. And this direction is equal to E21 times U plus E22 times V plus E23 times W, and so on. So this is just taking this formula and then isolating out the camera frame and putting it in matrix form. And so then, here's the trick. And so this is what we looked at to lead the video, that xyz times the Cartesian frame is equal to the coordinate xyz. But also, we know that this part right here, the Cartesian frame, can be written as this matrix times the camera frame. And so, here's our Cartesian frame, here's our camera frame. And so the Cartesian frame equals this matrix times the camera frame. And so we can instead do a substitution and say that xyz times the Cartesian frame is equal to this matrix times the camera frame. And then, this is what always makes me uncomfortable, is this matrix is exactly what we want, is that this matrix is taking coordinates in the Cartesian frame, and when you multiply them, it's going to be the same coordinates in the camera frame. And so if we could solve for all these coefficients, then this matrix would be exactly what would convert us from the coordinates in the Cartesian frame. The product of these two would then become coordinates in the camera frame. And so this part here always makes me uncomfortable, but actually it helped me a lot to work through this slide right here. This will come up later, what it means to take this vector and multiply it by this 4 by 1 and this 1 by 4, and that we end up with in this case, Cartesian coordinates. So that's the trick, that may not seem, it may be the next slide sounds even trickier to you, but the next slide seems okay to me. The next slide says that when you've got a system of equations like this, 1, 0, 0 equals E11 times U plus E12 times V plus E13 times W, that there's just something called Cramer's rule. That's just a formula for solving this. So E11 is equal to the cross product of the Cartesian x coordinate with the V from the camera frame dotted with W from the camera frame divided by U cross V from the camera frame dotted with W. Now, this formula is, a hard-fought formula by, someone who really likes linear algebra, but it's a formula for how to solve these sorts of equations. It's called Cramer's rule, and so with that, we can actually plug in, what we know about the camera frame, because remember that was our previous thing, was solving for the camera frame, and by plugging in the camera frame, and this is part of kind of one of the reasons we have the conventions we do, a lot of these terms drop out and get simplified. And so if we take the camera frame we know, if we start with this and say we need to know these coefficients, and we take the camera frame we derived in the previous video and we apply Cramer's rule, then we actually get a really simple matrix. And this is the really simple matrix. And this is the camera transform, this matrix right here. So that's it. This is your next 4x4 matrix. Is these coefficients from these components from the vectors of the camera frame. And then you see some of these are x. This is very tricky here. This is x u dot x. That means the x component of the u basis vector for the camera frame. This is u dot t. You see, this is a small dot. It's like lower. It's towards the bottom, and this is towards the middle. And so this is using the dot product of u with the vector t, and t is the difference between the origin of Cartesian minus the origin of the camera frame. So again, this bottom row, this is using dot products, and these top 9 values are saying the y component of u, the y component of v, and so on. So dot products and then just accessing individual components. So once again, I've like every other time I've taught this class, I've looked at these slides for an hour to feel comfortable, and every time I say, oh, it works, but it's this part right here where we can substitute in, take out this Cartesian frame and substitute in this matrix in the camera frame. And I just really have to think about what these things are under the covers and whether we really have the right to do it. And every year I convince myself that we do. And then once we have that, it's just a matter of solving these coefficients using Cramer's rule and using the camera frame that we already established. So that is the second matrix that we've derived, which is the camera transform. But of course, in our big schematic, the camera transform is actually the very first one. So we've now calculated this camera transform right here, and we've also calculated the device space transform. And so the only one we have left is this view transform, right? If I can select it, well, this one right here. Okay, I'll see you guys in part 5.